everyone, welcome back. Okay, so previously we were talking about all the different hybrid orbitals that can form. So we use these hybrid orbitals when describing compounds that have more than two atoms in it. Okay, so pretty much all the most common compounds we will encounter that you'll see, they'll have these common examples here. So linear for two electron domains, we have sp hybridization. Some examples are beryllium difluoride, or beryllium fluoride, carbon dioxide, nitrogen gas, trigonal pointer, three electron domains. So we should have three orbitals to form like three bonds, or a lone pair orbital, sp2. So common examples are Bf3, carbonate ion, and ozone. Four electron domains, we have tetrahedral arrangement of electrons, so four orbitals or four bonds, sp3, hybridized, CH4, sulfate, ammonia, and water. Okay. We move up to five electron domains. We have a trigonal bipyramidal, sp3d for hybridization, for five orbitals for five bonds, so P of 5. Monochlorine or chlorine trifluoride, and a triiodide ion. And then lastly, octahedral, when we need to form six bonds, we have the hybridization, sp3d2 for six bonds. So sulfur hexafluoride and xenon tetrafluoride are common examples of octahedral geometry. Okay, so let's do some examples now, so we can kind of think about how these hybridizations, how to apply them, okay? So, determine the hybridization of the central atom in oxygen, hydronium ion, tellurium tetrachloride, and iodine tetrachloride ion. Okay, so for the oxygen atom, remember we like to draw it with a double bond here, but in the next set of lecture notes, we'll see why maybe this representation is not the complete picture. But usually we draw like this. So we look at any oxygen atom, right? There's going to be three electron groups around it. Okay, so just look at one oxygen atom. Here we go. We have a lone pair, that's group 1. Another lone pair, group 2. And then this double bond here, that's group 3, so 3 electron pairs, or electron groups. So we say, remember, 3 electron groups, it's going to be trigonal pointer, so sp2 hybridization. Like that. And then the geometry is trigonal pointer. Okay? All right, so this in this example, oxygen is trigonal pointer. Let's move on to hydronium. So hydronium is like water, except we have a plus charge, so it's sort of like ammonia. So we have oxygen in the center here, hydrogen like that, and then there's a lone pair on top of the oxygen along with a positive charge here. Okay, so we count the electron domains around oxygen. We have 3 hydrogen atoms. So 3 plus a lone pair, 4 groups. So here we have 4 electron groups. Okay, and then it's going to be sp3 hybridized. All right, and then we would call this a tetrahedral geometry. So that's pretty much all we need to be able to do for elements like this, and for compounds like this. Okay, let's move on to the next example, tellurium tetrachloride. So tellurium, we haven't seen tellurium before, so let's calculate it. Tellurium is in the same group as oxygen and sulfur. So tellurium will have 6 valence electrons, and then we're going to add that to 4 times 7 of the valence electrons for chlorine. So we get 28 plus 6, which is 34 electrons. Okay, So let's write tellurium as the central element and position the chlorines around it. So right now we have 8 electrons. So let's fill the octets for chlorine. So right now we have, if we count each of the octets around chlorine, we get 8, 16, 24, 32. Now we need an extra lone pair, so that's going to go on to the tellurium here. So tellurium can expand its octet. So we expand the octet for tellurium because it has more valence electrons than an octet would have. So here we count the domains. So 1 lone pair, that's 1. Then 4 bonds, that's 5 electron domains. Okay. On the central atom, tellurium. Okay, so we say that if we go back up here, 5 electron domains, sp3d hybridization. Okay, and what is this geometry going to be? Trigonal bipyramidal. Let me see if I'm spelling it right. Okay, and we have a trigonal bipyramidal. So I think we're just going for that. So just a little bit of hybridization. So trigonal bipyramidal, 5 electron groups. All right, now let's write the last example. Draw the last example. The iodine example. Okay, so iodine is in the same group as chlorine, so 7 valence electrons plus 4 times 7. But for the other chlorine atoms, but we also have a negative charge, so we had to add additional +1 for the additional electron, and that gives us 36 electrons in total. So in this case, iodine will be our central atom, so let's draw iodine in the center there. And then for this molecule, it looks like we're going to have 6 bonds, or 6 groups around it, because we have a total of 36. So if we draw all the electrons around the atoms surrounding iodine first, we get 32 electrons distributed to chlorine and the bond around iodine. So we need 4 more. So we're going to add them on to iodine. And here we end up with the square planar complex or square planar geometry. So this has 1, 2, 3, 4, 5, 6 electron groups because of the 6 domains around it. So 6 electron domains. Okay, and then for that geometry, we will have a hybridization of sp cubed d squared, so sp3 d2, like that, and this is an octahedral electron geometry. Okay, so hopefully that gave us some practice in assigning hybridization and seeing how many electron domains and relating that back to the electron geometry. Okay, so now let's go on to the next exercise. We're going to draw the hybrid atomic orbitals for formaldehyde and then for acetylene. Okay, so first is formaldehyde. So let's assign all the hybridizations here. Hydrogen is not hybridized, so it's an s orbital for H hydrogen, an sp2 orbital for carbon because it has 3 electron groups around it, and same thing for oxygen. If we look at the electron groups, sp2 hybridized. Okay, so first we should draw, let's just draw our atoms looking down the CO bond. So we're going to have a carbon here. Let's draw an orbital for the sp2 orbital, and then we draw oxygen here, which with its sp2 orbital going to overlap the oxygen atom here. Okay. Boom, 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 boom. Okay. So I actually drew it a little bit wrong here. So one thing we want to remember that the hybrid orbitals, when we look at these hybrid orbitals, how we draw them is we don't necessarily show the lobes at the other side. If we look at here, so what we do is just imagine there's a small lobe here representing well, it actually might be better not to draw. Let's not draw it for now. Okay, so there's the here's the overlap of the sp2 orbitals. Okay, and then we're going to have two more, one over here and one over here, and this is going to hold the lone pairs as we've seen in our Lewis diagram. Okay, so we could think of this as the internuclear axis. Okay, just like how we drawn it in the other pictures. So this is an axis, the bonding axis. So here's going to be our bonding axis. Okay. All right. So now for oxygen and carbon, there's going to be a p orbital that's not going to be bonded, right? So carbon will also have the other sp3 orbitals here. And what's connected here are the H atoms. So we're going to draw a bonding interaction there. And a bonding interaction for the sigma bond for the other hydrogen, like that. So, and then we're going to draw the lone p orbital that's involved in the pi bond. So here's the pi bond. We're going to have an electron in this orbital, an electron in this orbital, but it's not going to be parallel spins. We're going to have to make it anti-parallel. So here's the pi bond, and this gives rise to the double bond. Okay, so this one will be a pi bond, and it's going to be from the p on the carbon atom to the p orbital on the oxygen atom right there. Okay, so these orbitals right here next to the oxygen, those are going to be sp2 hybridized, and it's going to hold a lone pair, so it's not a bond, it's an orbital. And then for these oxygen atoms here, the carbon and hydrogen bond, we can say it's a sigma bond composed of the carbon sp2 orbital to the hydrogen s orbital, like that. And then lastly, this bond over here is the sigma bond, so another sigma bond. CsP2 to oxygen sp2, like that. Okay, so that's how we draw the picture for formaldehyde. And you know, these pictures I'm not going to grade, you know, based on artistic talent. Just make sure you get the point across and you kind of match the picture I've drawn, and then you'll be okay. All right, to wrap up this first half of chapter 10, let's go on to the next exercise, but it's going to be a little tad more difficult because, let's count the bonds here. So in this molecule, we have 3 sigma bonds. If we count from in the picture we have just drawn, 3 sigma bonds and 1 pi bond, okay? So you may have to answer questions about that. So make sure we can identify the type of bonds we have drawn. All right, let's move on to acetylene, a gas molecule found in acetylene torches. You know, maybe to grill things, cook things, or just light a torch. Okay. So first, let's count how many bonds we should have. So in this molecule, we're going to have 1 sigma bond. For the CC bond, okay, and 2 sigma bond for the CH bonds, okay, so 2 of those, and then we're going to have 2 pi bonds for 2 pi bonds, for the triple bond. Okay, so those are 2 additional bonds come from 2 pi bonds. Okay, so let's draw this molecule right now. Okay, so remember for acetylene is a triple bond, so around each carbon atom there is 1 group, 2 group, so 2 electron domains. So this is going to be sp hybridized. So if we remember what sp hybridized looked like, we can go back up to our picture of orbitals. We're going to draw something that looks like similar dumbbell shape for sp. So we're going to do that for carbon now. So carbon, and then, so let's make this kind of circular here. Carbon and carbon. Okay, so here we have the pair of electrons being bonded for the sigma bond, and then for the for each of the carbon atoms, there's going to be another orbital that's overlapped with a hydrogen orbital from the 1s. So this is the H, and then this is going to be a little more spherical, H here. Okay, so I drew the sigma bonds for the molecule. So now the rest of the bonds are going to be p orbitals. So there's going to be 1 set along the y-axis, and then 1 set along the x-axis. So we could draw them 2 different colors here. It's going to be another set pointing out perpendicular to the first set of p orbitals. Okay. So like so. Okay, so the first set of p orbitals is going to be perpendicular here. So let's put it like this. So they're going to be lined up to the red set of red p orbitals. And then there's a purple set of p orbitals that are purple, and those are going to be lined up to the ones perpendicular to the set of p orbitals in red. Okay, so these are now going to be linked here and here. So I kind of drew different lines to indicate different orbitals. Okay, so let's label the orbitals here. So we have a sigma bond here, CSP to HS, and we have 2 of them here. CSP to the 1s orbital of the hydrogen. And then we have a, right here, we have the sigma bond, the CC bond, CSP to the CSP bond. So that's very good. Okay, and then we have 2 sort of pi orbitals here. We could label them, so if we label this direction the x-axis or the z-axis, we could label these pi orbitals as x and y. Okay, so let's label this one as the y, pi y. So it's going to be a pi bond between the CPY and the other CPY. Okay, so that's a pi bond on the y-axis. And then this red bond here, let's mark in red. This bond here is going to be so we could label it here, another pi bond in the x direction, so it's going to be from the px to px, so we could label it as the cpx to cpx p orbital bond. So that's a pi bond. Okay, so we have 2 set of pi bonds, pi x, pi y, and then sigma bonds. So 3 sigma bonds, 2 pi bonds. So that's how you would write the one for acetylene. Okay, all right. So let's end. This is the end of chapter 10, part 1. We're going to pick up in the next video on part 2, where we talk about the other major theory of bonding, molecular orbital theory. So I will see everyone next time.